Welcome back to Studious. Today, we are peering through the microscope to uncover the architecture of loose connective tissue, a structural blueprint that serves as the body's foundational biological ecosystem. To understand human anatomy, you have to understand what holds it all together. Connective tissue is a broad category of tissue found at virtually every internal and external site within the human body. Its primary jobs are to provide mechanical strength, vital elasticity, and crucial metabolic support to all other tissues. Think of it as the ultimate biological support network. Without it, our epithelial layers would starve, our organs would lack structure, and our immune systems would lose their most critical battlefield. In this video, we will explore this microscopic metropolis, breaking down its inhabitants, its scaffolding, and the environment they live in. If you want to master histology, you are in the right place. Let's dive in.
Before we zoom in on loose connective tissue, we need to look at the larger family tree of connective tissues. Connective tissue can be broadly classified into three main categories based on its composition and the organization of its extracellular matrix. First, we have embryonic connective tissue, which is primarily found in the developing fetus. Second, we have specialized connective tissue, which includes highly adapted tissues like bone, cartilage, and blood. Finally, we have connective tissue proper, which acts as the general packing material of the body. Loose connective tissue falls precisely under this category of connective tissue proper. You will often hear it referred to by its alternate name, areolar connective tissue. It earns this classification because of its specific, highly abundant cellular components and its loosely organized extracellular matrix. This loose organization is no accident. It is functionally necessary to allow nerve fibers, blood vessels, and immune cells to travel freely through the tissue.
To truly understand the areolar ecosystem, you must view it as a tripartite structure, a bustling city built on three fundamental pillars. First, we have the cells, which are the active inhabitants of this ecosystem. This cellular content is highly abundant and incredibly varied, featuring key actors like fibroblasts that build the environment and adipocytes that store energy. The second pillar is the fibers, serving as the architectural scaffolding. These are structural proteins, primarily reticular and elastic fibers that provide both mechanical support and essential recoil so the tissue doesn't tear. The third and final pillar is the ground substance, the environment itself. This is a viscous, clear medium that suspends the entire ecosystem. It is composed of complex carbohydrates and acts like a biological shock absorber. Together, cells, fibers, and ground substance work in perfect synergy to maintain tissue homeostasis, facilitate nutrient diffusion, and provide a stage for immune defense.
Let's look closer at the scaffolding, starting with reticular fibers. These fibers form a delicate, branched meshwork that physically supports the resident cells and provides vital mechanical strength to the tissue. From a compositional standpoint, reticular fibers are essentially thread-like strands composed of type 3 collagen fibrils. Where do they come from? They are manufactured and secreted directly by the resident fibroblasts living within the tissue. While they are present throughout loose connective tissue, reticular fibers are heavily deployed in specific zones. You will find them primarily in areas that require rapid, new extracellular matrix production. Because of their thin, branched nature, they are the first responders of tissue scaffolding, laid down specifically at sites of active wound healing and early scar tissue formation. Over time, in a healing wound, these delicate reticular fibers are often replaced by thicker, stronger type 1 collagen, but they remain the essential first step in rebuilding a damaged architectural matrix.
Our next structural component is the elastic fiber, the element responsible for flexibility and recoil. If collagen provides the tensile strength to resist pulling, elastic fibers ensure the tissue can snap back to its original shape. Structurally, these fibers are built primarily from a highly resilient protein called elastin. Rather than running in simple parallel lines, elastic fibers are arranged in a complex three-dimensional branching network. Crucially, they do not act alone. They are intimately interwoven with sturdier collagen fibers. This partnership is brilliant. The elastin allows the tissue to stretch, while the collagen locks in a maximum stretch limit to prevent the tissue from tearing under excessive force. Because of these unique properties, elastic fibers are deployed heavily in anatomical structures that must frequently adjust their shape and volume. You will find them abundantly in the walls of blood vessels, within the expanding tissues of the lungs, externally in the dermal layer of the skin, and lining the urinary bladder.
Surrounding the cells and fibers is the ground substance, a component that is incredibly vital, but often completely invisible to students looking through a microscope. This invisibility is due to the H&E reality. During routine hematoxylin and eosin staining, the ground substance is dissolved and lost, leaving what looks like a virtually empty white background behind the cells and fibers. However, the chemical reality is quite different. In living tissue, ground substance actually occupies the largest physical proportion of the loose connective tissue. It is a clear, highly viscous, gel-like substance characterized by an extremely high water content. This gel is synthesized by fibroblasts and is composed of a complex mixture of proteoglycans, glycosaminoglycans, and structural glycoproteins. This hydrated gel is crucial for survival. It allows dissolved gases, nutrients, and waste products to diffuse easily between blood capillaries and the cells, while simultaneously working alongside elastic fibers to provide exceptional tissue flexibility.
Now let's meet the most important architects of this space, the fibroblasts. These are the infrastructure builders of connective tissue, but they exist in two distinct functional states. In their active state, they are called fibroblasts. These are the cellular workhorses responsible for continuously producing the fibers and the complex carbohydrates that make up the ground substance. Because they are so actively engaged in secreting matrix components, they reside tightly against collagen bundles, making their pale cytoplasm very hard to distinguish under a microscope. However, when their building tasks are complete, they transition into a dormant, inactive state known as a fibrocyte. Structurally, fibrocytes are much smaller and possess fewer cellular processes. In H&E stains, you can easily identify an inactive fibrocyte by looking for its nucleus, which appears as a condensed, deep purple, disc-like, and elongated structure. If tissue damage occurs, these resting fibrocytes can reactivate into fibroblasts to begin emergency repairs.
Maintaining this biological metropolis requires a constant source of renewal, which is provided by mesenchymal stem cells. Found scattered within the loose connective tissue, mesenchymal stem cells are a specific, multipotent type of adult stem cell. They are essentially the blank slates of the areolar ecosystem. Their primary role is to ensure the tissue can adapt, repair, and regenerate over a human's lifespan. Through lineage-specific differentiation, these stem cells can yield brand new fibroblasts to replace those that have aged or died, ensuring the continuous production of the extracellular matrix. Beyond just fibroblasts, mesenchymal stem cells are incredibly important for vascular health. When a tissue grows or requires more blood flow, these stem cells differentiate to help generate the necessary cellular architecture for forming entirely new blood vessels, a process known as angiogenesis. Without this hidden reservoir of stem cells, our connective tissues would lose their ability to heal from even the most minor injuries.
Sharing the neighborhood with fibroblasts are adipocytes, or fat cells, which are dedicated to energy storage and thermoregulation. There are two primary types of adipose tissue, white and brown. White adipose tissue is the dominant form in adults. It acts as structural packaging around internal organs, cushions peritoneal structures, and forms the insulating subcutaneous layer beneath our skin. Histologically, white adipose looks like a meshwork of empty, interconnected spaces. This is because the massive lipid droplet inside each cell is washed away by the chemicals used in slide preparation, leaving only the thin rim of cytoplasm behind. Brown adipose tissue, conversely, is highly prevalent during fetal life, but diminishes significantly within the first 10 years of life, leaving only small amounts in adults. Instead of just storing energy, brown fat's primary function is to actively generate heat to aid in body temperature regulation, which is why its histological appearance is a much denser, specialized fat accumulation packed with mitochondria.
Loose connective tissue is also a major immune battlefield, guarded by a widespread network of macrophages. These cells originate as monocytes in the blood. They migrate into the tissue, mature into large phagocytes, and act as garbage collectors, clearing dead cells and debris, while also presenting foreign antigens to white blood cell lymphocytes. Depending on where in the body the connective tissue is located, these macrophages take on specialized local identities. In standard loose connective tissue, the resident macrophages are simply called histiocytes. If you move into the connective tissue of the liver, they differentiate into Kupffer cells, which act as the resident defenders of hepatic tissue. In the lungs, they become alveolar macrophages, deployed right at the air-tissue interface to consume inhaled pathogens. And in the central nervous system, they are known as microglial cells, acting as the highly specialized mediators of the brain's inflammatory response. It is a highly coordinated, region-specific security grid.
Alongside the macrophages, we find the chemical alarm bells of the immune system, mast cells. The origin path of a mast cell is a multi-step journey. They initially arise from hematopoietic stem cells deep inside the bone marrow. They then migrate as immature cells through the peripheral circulation, only reaching full maturity once they exit the blood and embed themselves inside the loose connective tissue. Mechanistically, a mature mast cell is heavily packed with large secretory granules containing potent vasoactive mediators like histamine and heparin. When triggered by an allergen or pathogen, they rapidly degranulate, releasing these agents which are critical for driving the inflammatory immune response and allergic reactions. Because environmental threats can come from anywhere, mast cells are strategically deployed in connective tissue throughout the entire human body. However, there is one strict exception. To prevent catastrophic inflammatory swelling in closed spaces, mast cells are not present in the brain and spinal cord.
When we look at a slide of loose connective tissue, we are seeing a symphony of biological activity occurring simultaneously. This ecosystem synthesis is what keeps our bodies structurally sound and immunologically safe. Picture it. Deep within the clear, viscous gel of the ground substance, fibroblasts are actively weaving and repairing the delicate type 3 collagen reticular mesh. Woven directly into that mesh are the elastic fibers, constantly stretching and providing structural recoil as the body moves and breathes. Navigating through this hydrated gel environment are the immune sentinels, mast cells chemically sniffing for allergens, and histiocytes physically patrolling for cellular debris and foreign invaders. And anchored safely within this complex matrix are the adipocytes, silently holding on to subcutaneous energy stores until the body needs them. None of these components function in isolation. A defect in the fibroblasts impacts the fibers. A loss of ground substance dries out the tissue, and an absence of immune cells leaves the entire ecosystem vulnerable to collapse.
So, where exactly in the human body is this tissue deployed? Loose connective tissue acts as a universal sublayer. You can find it acting as the foundational cushion immediately beneath the epithelial tissue of virtually all organs that have external openings. In the skin, it is located directly beneath the epidermis, forming the papillary layer of the dermis. Deeper inside, it forms a highly specialized layer known as the lamina propria, which directly lines our digestive and respiratory tracts. It is also the primary connective tissue supporting the mucous membranes that line our reproductive and urinary systems. But it isn't just restricted to external borders.
Inside the body cavity, loose connective tissue forms the internal stroma, the supporting framework of our major glands. And it makes up the vast, delicate mesentery that wraps around and anchors the intestines to the abdominal wall, providing a highway for blood vessels to reach the gut.
Understanding this tissue isn't just an academic exercise. It has life or death clinical applications, particularly in oncology. Let's examine carcinoma and its relationship with the lamina propria. Carcinomas are cancers that originate strictly from the surface epithelium. The lamina propria, a classic and prominent layer of loose connective tissue just beneath the epithelium, serves as the definitive reference point for pathologists determining a cancer's stage and a patient's prognosis. In a stage 1 non-invasive cancer, such as early urogenital cancer, the malignant tumor remains entirely constrained within the epithelial layer, sitting above the basement membrane. Because there are no blood vessels in the epithelium, the risk of spread is low. However, stage 2 signifies an invasive cancer. This occurs when the tumor acquires the ability to breach the basement membrane boundary and completely penetrates into the loose connective tissue of the lamina propria. Once in this vascular-rich connective tissue ecosystem, the cancer can easily metastasize through the blood and lymph.
To wrap up, let's review our loose connective tissue architectural cheat sheet. Remember the cells? Fibroblasts are your active builders, while fibrocytes are dormant. Adipocytes provide white or brown fat storage, and mesenchymal stem cells act as your regenerative source. Your immune defense relies on histiocytes, your local macrophages, and mast cells, the chemical responders completely absent from the CNS. Your scaffolding consists of reticular fibers, forming a type 3 collagen mesh for wound healing, and elastic fibers providing a 3D network of recoil. All of this lives in the environment, a clear, viscous ground substance made of proteoglycans that is famously lost in standard H&E stains. Clinically, this tissue forms the vital lamina propria, and a tumor breaching into this space defines the terrifying transition to invasive carcinoma. That concludes our deep dive. Thank you for studying with Studious. If this helped you conquer histology, please leave a like, subscribe for more content, and keep studying hard.